last time. At the moment, you can't speak and you can't be seen. If you did want to speak, though, all you need to do is hit that raise hand button, and we'd find you and unmute you, and then you can talk. So feel free to do that. But as per last time, please keep those questions and comments coming in on the Q&A, and we will we'll get to them as Jamie presents or I cover off a few things. And any perchance that we don't get to, which I'm pretty sure we'll get to any that come in, we will take those over to next session. And that does bring up what we're doing next session, which we do have some specific installation examples and challenges and how to deal with tricky situations and lots of real world photos and the like. But we do offer the opportunity for you to submit sites or plans, or even just a street view location or a location where you're having some challenges, or you've seen a barrier system that you have questions about or the like. And we will tackle those live and sort of tap into the different knowledge from Jamie, and even others might have their say. So please feel free to submit that either now or via email, or pop it into the Q&A, or email it through to me at any point, and we'll get to it. I'll remind you about that again at the end, but it's a great opportunity. Thank you for your assignments. Quite a few people got their assignments in, and overall really great work in finding those products, finding some information about them, comparing them to like products. So you did really well. A few people just need to make sure they're careful about which products are legacy products and which are accepted for use products in New South Wales. So even though it's on that website, you need to see which what it is categorized as. So so some of your products are legacy now, so just out there being maintained and the like, not the new installations. So a couple of people got tripped up on that, but overall really great level of knowledge out there, and a good bit of work in that assignment. And for some of you, it may have been the first time you actually went and looked at one of the product sheets. And we definitely encourage you to do that all the time. And others do that run-of-the-mill exercise in their day-to-day tasks. So today we're going to cover off some design considerations. And when I introduced Jamie in the first module, I mentioned that he does a lot of barrier design, a lot of work around that, and then assessing different barrier design setups and installations. So Jamie's done many years of barrier design, and he's going to share some of the sort of fundamental principles around barrier design and things to be considered. And then after that, I'm going to jump in with a bit of information about motorcyclists and barriers, which is a question that's come up with this group already, but also is very much something that a lot of the community is interested in, and it's good to arm ourselves with a bit of information around that. And there's a few things we can do. So I'll pause there and see if anyone wants to type a question in. I'll pop their hand up before we even get started. No, looking pretty good. I think everybody's happy and excited to hear from Jamie. So I'm going to hand it over to you, Jamie. I'll pause you anytime any questions come in, and I'll also I might pause it a little bit along the way and ask the group a couple of questions. So over to you, Jamie.
Thank you, Ken. You're looking at the right view there.
Yep, looking good.
Thank you, and good afternoon, everyone. Today, I'd like to take you through some of the basics around barrier design. The key reference when we're talking about barrier design is Austroad's Guide to Road Design Part 6, which we've mentioned previously, and it does provide a quite long-winded process for designing barrier treatments. It's something in the order of 16 steps. I wouldn't expect anyone to go through it 1 to 16, but what it does do is capture all of the important steps, and I've picked out some of the more important ones to discuss with you today. So there's the Austroads Part 6, which is recently updated. There is an RMS supplement to the part. It has not yet been updated based on the new part. And there, in fact, is a comment on the RMS website saying that the new Part 6 is yet to be adopted in New South Wales. I expect that it will be very shortly and that the supplement will be updated at the same time. There is a bunch of RMS standard drawings around barrier treatments, typical details, connections, transitions between different systems, these type of things. The supplier's manuals and drawings for proprietary products are a useful resource, especially if you're in a tricky spot where one barrier system might provide a better outcome than another. It can be useful to look to drill down to the finer detail and look at the detail available at the supplier's websites. Also encourage you to talk to the suppliers as well, especially in those tricky situations. The RMS website has a list, and we saw them last time with Evan, a product acceptance sheet for each accepted product. TCU, technical conditions of use, is the term that Austroads uses, and the TCUs are basically reproduced as a New South Wales product sheet. There's a great list of frequently asked questions on the website as well, which captures a lot of the key design considerations, common questions. Now, before we start designing a barrier, we really want to think about what is it intended to do? And that really narrows down the suite of products that we have to choose from. Is that the roadside in a median where we're interested in preventing head-on crashes, at a bridge perhaps, or maybe it's at a work site where we're primarily concerned about the safety of the workers behind rather than the occupants of those errant vehicles. So at the roadside, we're really concerned about the consequences of that single vehicle run-off road crash. So the barrier only needs to be able to be struck safely from one side. It's perhaps not of a particularly high containment level as we'd find at a bridge. So you can see some guard fence examples there with some redirective energy absorbing terminals. On a windy motorcycle friendly route, you might see a barrier like this with some motorcycle add-ons, and Ken will talk to you about these type of things in a little while. You might see a wire rope barrier at the roadside, as you can see there. In the median, we need a barrier that can be struck safely from both sides. So wire rope is a popular choice. You might have a back-to-back guard fence installation there. We have a G4 or similar. It might be a flexible W-beam back-to-back system. On a high volume, high speed road with a lot of trucks like this urban freeway, we might use concrete. Now, it's the least forgiving system we have, but in a relatively constrained environment like this where impact angles are likely to be low, it's a good option. And we really are concerned at what might happen if a larger vehicle did penetrate a median barrier due to the high volumes at this location. On bridges, we typically beef things up, so you can see a tri-beam installation there, steel barrier. Well, often we'll see a concrete barriers or a concrete and steel combination. So what is our barrier? Doing? What's its purpose? That helps us make some decisions around the product that we choose. And Evan took you through the list of accepted products last module, and it is constantly evolving, and it's undergone quite some change in the last little while with the transition to MASH. With our longitudinal barriers, we class them as rigid or semi-rigid or flexible. Every barrier has an end treatment. It might be an end terminal, like a guard fence end treatment. It might be a crash cushion or impact attenuator that we might use at the end of a concrete barrier, for instance, or a bridge pier. We might have a point protector, like the Raptor crash cushion that we've seen, particularly useful in highly constrained locations where we don't have the space for a longitudinal system. And our installation might be permanent or temporary. So we have products classified as permanent and others classified as temporary. And any installation might be of a permanent nature or a temporary nature. So it is even sometimes the case that we might use a permanent barrier in a temporary situation. We might have a temporary transition or traffic switch as part of some roadworks that's going to be in place for a year or two. So it's a temporary situation, I suppose, but we sometimes make the decision to use permanent systems. And rigid barriers, the least forgiving system in terms of risk to vehicle occupants. You can see there some examples on bridges where we've got concrete barriers. We are concerned about what will happen if a heavy vehicle does penetrate that barrier and ends up below, perhaps on a roadway or a rail line or in a stream. So the secondary consequence is often of greater concern than that single vehicle run-off road crash. They deflect by very little, next to none. They're massive lumps of concrete. They're anchored to a structure often, so they deflect by next to nothing. As a result, they don't incur much damage when they're struck. That's a good and bad thing. It's great in terms of maintenance. They rarely require maintenance intervention, and therefore their ongoing cost is low. But if and when they are struck by smaller vehicles, there is a greater risk of injury to those vehicle occupants. So because of that, we need to be mindful of where we locate rigid barriers, not at locations where we might expect an impact at a relatively high angle. So perhaps off the back of a curve, we need to be conscious of the distance from the edge of the road that a rigid barrier might be located, so as we're not opening up that possibility for larger impact angles. Another benefit is that they can and do contain larger vehicles, and they can be engineered to contain as large a vehicle as you would like. Stepping down in terms of rigidity, we have the semi-rigid category, G4 on the left, Thri-beam on the right. Now I'll note that both G4 and the public domain Thri-beam products are now legacy. There are some proprietary Thri-beam products that are accepted for use. Semi-rigid systems, they do deflect by a relatively small amount. Because of that deflection, they have some sort of cushioning effect on the occupants of the errant vehicle, so they're more forgiving than rigid systems in that regard. They usually remain serviceable after an impact. They will incur some damage, but not enough that they are rendered ineffective for a subsequent impact. You can transition a semi-rigid barrier directly to a rigid system, so that's a great thing on a bridge approach, for instance. They are more easily applied in constrained locations, and that's particularly in comparison to wire rope systems. They can be curved relatively tightly. Their minimum length requirements are less prohibitive than some other systems. Flexible barriers, the most forgiving and the best in terms of vehicle occupant safety. On the left, we have a wire rope system. Now it is a now superseded system. I need to get a new MASH tested picture there. That's an old flex fence 4-rope system that there is a lot of on the New South Wales network. The newer cousin of wire rope is the flexible W-beam barrier, which at first glance looks very similar to a semi-rigid barrier, but the notable difference is that there isn't a block between the post and the rail, and of course our posts are relatively weak, so the system performs largely by the tension developed in the system rather than the resistance provided by the posts. Flexible systems deflect by a fair amount. As a result, they are forgiving on the occupants of the errant vehicles. Wire rope is the best in that regard, but the flexible W-beam systems aren't far behind. The barrier may be rendered ineffective by a single impact, and that particularly applies to wire rope systems. A significant length of barrier can be damaged when a wire rope is struck. You might be talking in the order of 50, 80 metres, something like that. The cables will lose tension, perhaps even be lying on the ground. So we can't be sure, or it's even unlikely that another impact in the same location that the vehicle would be contained. Wire rope is difficult to apply in constrained situations, horizontal curves or short lengths between driveways, for instance. Flexible W-beam system is better in that respect, but not quite as good as the old G4. So it is important to have the ins and outs of the different categories of barrier systems in your mind before you're commencing a barrier design. And a few quotes here from some of the relevant guides around design and choice of barrier systems. Part 6 does say that a barrier should only be installed when the barrier reduces the risk associated with the roadside. Comments along those lines used to be a much bigger feature of that part. It's generally now accepted that a barrier, and particularly a flexible one, provides a better safety outcome than not providing one. That said, there are some design things that we need to do to ensure that we don't introduce a risk to road users when we install a barrier. AASHTO talks about whole of life cost, and that the best solution is the one with the lowest whole of life cost. There's been a lot of work done in Victoria around comparing the different flexible systems in terms of whole of life cost, and that is one big attraction of the flexible W-beam products over wire rope, because they don't require that maintenance intervention every time they're struck. Those systems are coming out on top by a reasonable margin, even though their installation costs might be higher than an equivalent wire rope. The general philosophy is to accept the most flexible system you can, subject to the constraints at the site. So there the hierarchy would be wire rope, then your flexible W-beam products, semi-rigid and rigid. When you're thinking about the decision to install a barrier and your barrier type, there are a few key things to keep in mind. Think about the speeds at your site. That will influence whether you need a barrier at all. We know in high-speed environments that the entire roadside area is of interest, and there is benefit in shielding roadsides continuously, even where there are no fixed hazards present. In a lower speed environment, a barrier may not be required or provide any great safety benefit. What is the consequence of barrier penetration? Is our worst case scenario just that single vehicle run-off road crash, or is there a secondary consequence that we need to be aware of? And if there is, this is where we typically beef up our containment level and go with a more rigid system. And know the ins and outs, the pros and cons of the different systems, the different categories of systems, and even the individual products within those categories to help you make informed choices. So for the next little while, I'd like to try and summarise a few of the key design decisions. These elements of design are captured in that design process that I referred to in the Austroads guide. The first thing we need to think about is what is our hazard? Identify your hazard. Where is it? How far from the road? How long is it? We use this term protected width. That is the width from the edge of our road to the furthest part of the hazard from the road. So The protected width is that area that we are looking to shield all errant vehicles from. It's not the width, the distance to the front of the hazard. We need to account for the width of the hazard itself as well. Length of need is the term that we use to describe how long a barrier needs to be to shield a particular hazard. We need to locate our barrier in relation to the edge of the road. We need to be mindful of our traffic lane arrangement, our existing and desirable shoulder widths and verge widths. Is there a curb in play that might influence our lateral, the lateral offset of our barrier from the edge of the road? Is our batter one that warrants shielding in its own right? Is it flat enough that we can install the barrier on that batter? We need to think about run out areas, and I'll explain that concept a little later. That might influence where we start and end a particular barrier. And we need to think about how we might transition to other barrier types. There might be existing barriers on a site that we need to match up to, or there might be other barriers of a different type proposed as part of the same project. It might be that we have a structure that warrants a high containment level barrier, and we need to either connect directly to that barrier or overlap in some way. So it's often the case that we'll go into a barrier design with a preference for a system. And I do encourage you to sort of think flexible first, but through experience, you'll identify that flexible systems are often difficult to achieve. So it's quite an iterative process. You can't simply adopt the barrier type that you might like, select the offset from the edge of the road that you might like. There's often a bit of back and forth, weighing up different options. We'll go through some of that over the next few slides. There are two distinct scenarios in barrier design. The first is a new roadworks project, a new piece of road, or a roadway where there's some other works happening, and we have the benefit, therefore, of survey and other design information. And you can see here we have an alignment plan drawing, which shows an upgraded roadway. We've clearly got survey, and our barrier is shown on this drawing here with a fairly minimal amount of detail. The type of barrier is nominated, wire rope safety barrier. Its start and end point, well, not at start and end point, it's points of need at either end, and we'll talk to that in a minute. Little other information. The offset of the barrier is not nominated, and that's because we're using a scale drawing. We can obtain those measurements from scaling or through interrogating the digital files. So it's typically the case that we have minimal detail shown on this type of drawing. There might be a schedule on the same drawing or on a different sheet that describes a barrier in more detail, but this is a typical example of a barrier shown on a roadworks drawing. The other situation is a barrier retrofit. We might have identified that a particular piece of road has a high incidence of run-off road crashes, as was the case here, and it was decided to install barriers around, isolated barriers around particular hazards that were considered high risk. In these situations, you typically don't have the benefit of survey. You might present your design on an aerial photo, as you can see here. And where that's the case, it's important to nominate some features that can be located easily out on the ground as reference points that our barrier can be set out about. So I won't go into the detail of this notation, but this is a sort of shorthand convention that might be used to describe the length of a barrier, where it sits in relation to the road, the type of system and terminals and so on. And you can see some different features nominated here as reference points, RP. So that's the critical hazard, perhaps the closest hazard to the edge of the road, and it's the set out reference point for this particular easy guard barrier. Here's another example of a barrier retrofit project, and this is a continuous barrier design job. So in many locations along this freeway, there were no particular hazards in close proximity to the road, but the entire roadside was considered hazardous due to the speeds and volumes along this length of road. So here we're not so concerned about how long our barrier needs to be. The art of the design in this case was avoiding all the services that were generally located where you might like to locate a barrier, and in locating barrier access points and designing overlaps and these type of things. Length of need. I mentioned length of need. That's how long a barrier needs to be to shield a particular hazard. It depends on a few things, on how far that hazard is from the road, and in particular, how far to the rear of that hazard. So that's this point here. You can see we call that our protected width. The location of the barrier in relation to the road, or sort of more to the point in relation to the hazard. The closer to the hazard the barrier is, the more easily it cuts off that run out line that you can see drawn there, and the shorter our barrier needs to be. Speeds influence our length of need. We typically find that at higher speeds, vehicles will depart the road or may depart the road at particularly shallow angles and reach hazards located a long way from the road. Flaring of barriers can influence their length of need, as can the road geometry. We treat straights and curved sections differently. So here you can see our length of need. And the other term that we've mentioned is our point of need, PON. That is the point at which our barrier becomes redirective. So it's not the very start of the barrier. Any barrier system or any barrier terminal rather has a portion that is not redirective, it's gating. If a vehicle strikes before that point, the terminal is expected to allow the vehicle to pass through. So it's not effective in terms of redirecting the vehicle. So the critical thing to understand is where is your point of need, point of redirection, and that's the point at which your length of need begins. It might be the case that a hazard is a hazard for one direction of travel only, or it might be that we have a two-way road and we need to shield it for both directions. So our total length of need in that situation would be our length of need for one direction. Here we've called it the adjacent length of need, plus the length of the hazard itself, plus the length of need for the opposing direction. So the sum of those three things is our total length of need, which is not quite our total barrier length. We then need to add these two gating portions at either end, which is some or all of our terminal length. So I hope that makes sense. In New South Wales, the angle of departure method has for a long time been adopted to determine lengths of need. The Austroads Guide talks about two methods, one being the angle of departure method, the other is the run-out length method. Now, a number of other states, including Victoria, use that run-out length method. It seeks to provide a corridor for deceleration when a vehicle departs the road and perhaps just misses the start of a barrier. The intention is that enough length is provided between the start of the barrier and the hazard for that vehicle to come to a stop ideally, or at least wash off enough speed to avoid a serious outcome. That method typically results in some shorter barrier lengths than the angle of departure method. So the angle of departure method is certainly a more conservative method and arguably safer method. It makes things easier as well geometrically to work out barrier lengths. You can see here that for different speeds, different departure angles are nominated. So at high speeds, it's only 2.9 degrees, which is a bit of a funny number, but that equates to a run out gradient of 1 laterally and 20 longitudinally. So that 1 in 20 ratio is what we would use to work out the barrier length in a high speed environment. So if I skip back a couple of slides, we have this vehicle run out line. This line is to be drawn at a certain angle from the direction of traffic, and that angle depends on our speeds and is our angle of departure angle.
And I don't think we were seeing your pointer on that one.
Sorry, Ken. I've got two screens happening here and I was using the wrong one.
All right.
So here we have our vehicle run out line, which on a straight piece of road, we construct that run out line at a particular angle from the direction of traffic. So our angle in here is to be taken from the Austroads guide. We choose the appropriate angle of departure based on our speeds. So in states that don't use the angle of departure method, the question always comes in, what's the magic angle? There is none. We have to explain this complicated run out length method. So I do like the angle of departure method. It does, however, result in some particularly long lengths of barrier. And I'll point out as well, it does result in a barrier length or a barrier that provides just as much length for the opposing direction as it does for the adjacent direction, as opposed to other methods which result in relatively short lengths on that opposing side. So despite what this drawing looks like, it looks like we have different angles here and here. These angles are the same, and your barrier is basically a mirror image on the approach and departure sides. This is for a two-way situation on a straight road. If we had a one-way roadway, we need to provide that same length of need for the adjacent direction. But at the departure end of the barrier, look, the typical situation would be to locate your point of need around about here, so in line with the end of the hazard. However, we can even squeeze things up a bit more if we're constrained and we had perhaps a driveway that came in here on a bit of an angle. We can shorten that barrier and adopt this angle B and assume that a vehicle isn't going to depart the road at anything like 90 degrees. The worst case angle that a vehicle might depart the road with any significant speed is something like 22 degrees. So that's this trailing angle column that we can find in the Austroads guide. So 22 degrees is the angle that we can use to determine where our trailing point of need can be located. On curved sections of roadway, we do things a little differently. Instead of constructing that line, perhaps I better qualify this. In some states, in most jurisdictions, in fact, it is the case that we would construct a tangential run-out line. So we'd continue a line on the tangent to the curve and project that to the back of the hazard. However, in New South Wales, I believe that we continue to use that additional angle of departure, so our 2.9 degrees, in a high-speed environment. And that's how we arrive at our barrier lengths. That is a difficult thing to determine on site. If you're doing a design in CAD, you can be constructing those lines on the screen and work things out, but to do that on site is quite the difficult thing. Now, we've talked about how long our barrier needs to be. Our barrier offset is how far from the edge of the road should that barrier be. Now, this does influence our length. So again, it is an iterative process. Our barrier offset and length of need are dependent on each, well, sort of interdependent. The Austroads guide provides some limited guidance on where we should locate barriers in relation to the road. It talks about 3 metres being a minimum requirement. We, of course, do install barriers on occasions at lesser offsets than 3 metres. The general consensus between the jurisdictions is that 4 metres is a good offset to achieve. That provides enough space for a vehicle to stop at the side of the road when one has to. So it might be a vehicle is broken down and it has to in an emergency situation. So 4 metres allows the vehicle to do that, for the occupants to open the door. It allows maintenance vehicles to pull up at the side of the road and do what they need to do, tow trucks and so on. We do need to limit our barrier offsets to the point where we don't locate them so far from the road that we're opening up that possibility of rollover, and also of vehicles striking those barriers at excessive angles, which would result in greater occupant impact severity and greater potential for the barrier not to perform because they're being struck at angles in excess of the crash tested combinations. So 4 metres is typically our desirable offset, up to about 6. It's sometimes the case on higher class roads that we might have the luxury of pushing out beyond 4. It might suit us to go beyond 4 because there are services right at the edge of shoulder or something like that. In those cases, I suggest you consider offsets up to about 6, but not more. 3 metres is that minimum requirement that the Austroads guides talk about. So that's Austroads Guide to Road Design Part 3 and 6. The 3 metre shoulder with a barrier at the edge of shoulder. Less than 3 metres, it happens all the time, and the risk of doing that really depends on the nature of your road and the length of the barrier. If it's a high-speed road where we want to provide opportunities for people to pull over in emergency situations or for maintenance purposes, we want to be looking at that minimum 3 metre offset. If it's a lower class road, or if our barrier is particularly short and there are opportunities for someone to pull over before and after the barrier, we wouldn't expect that someone would have to pull up at that particular location. We often see that barriers are installed at lesser offsets, and sometimes at as little as 1 metre or even 0.6 of a metre from the edge of the traffic lane. It might be that we have a structure and our unstructured barriers are only that bare minimum, and we're transitioning a barrier into those. So it is okay to dip below those minimums on occasion, but you really need to weigh up the risks of doing that and think about what it means for the travelling public and providing opportunities for them to pull over in a safe way either side. You can mitigate the risk of providing barriers at less than desirable offsets by installing refuge bays at regular intervals. It might be that if you do have a long length of barrier at an offset of less than 3 metres, you provide some refuge bays. So you locally widen the formation and you flare your barrier out to provide a 4 or 5 metre wide bay where someone can pull over at the side of the road if they need to. There are lots of things that feed into your choice of barrier offset. Is there curb? Where is our hinge point? The point at which our formation tips over, the change from our verge to our batter. Different barrier systems have different requirements in terms of their offset to hinge points, and those requirements are about providing enough lateral support to the barrier system, to the posts of the system, and also containing deflection. It is desirable to contain the full dynamic deflection of the barrier system within the verge, but that, especially in retrofits, is it's rarely achieved, if I'm honest, and that's because it would require a hell of a lot of earthworks to do that, or to compromise your barrier offset to the point where the barrier is located really close to the road. So there are some trade-offs that are made in that respect. There's a little formula there, Dmax minus 1.3 metres, which probably doesn't mean anything to you, but Dmax is the deflection of a wire rope. And it's a little formula that's sometimes used. If you know how much your barrier might deflect and then subtract 1.3 metres from it, that will ensure that one set of wheels of the impacting vehicle, the inner set of wheels, will remain on the verge. The left hand, if you're running off the road to the left-hand side of the vehicle will travel out into mid-air beyond the hinge point, but the right-hand set of wheels will be on solid ground, and the likelihood is that the vehicle will be redirected. You need to think about table drains and other features where the grade changes and the interaction between barrier systems and these changes in grade. Shy line offsets. The shy effect, shy line is about the shy effect, and that occurs where we have objects located close to the edge of the road that encourage motorists to shy away from that object. So it's about not creating surprises to approaching motorists. And if we do have a barrier being located within a shy line offset, and there are prescribed numbers for different speeds, if we go within that shy line, we need to ensure that the terminal is located outside the shy line and that we have a gradual flare as we approach that point where the barrier is located, particularly close to the road. Where we are flaring barriers, we need to be mindful of maximum flare rates. So that's about providing a good visual cue to motorists and not creating those surprises through the shy effect, and also limiting the impact angles with the barrier. If we have a significant flare rate, there is a greater opportunity for a vehicle to strike at a more severe impact, and therefore for there to be a greater impact severity to the occupants. So lots of things that we need to keep in mind and weigh up when we're selecting our barrier offset. So the important thing is to understand your cross section. If it's a retrofit job, get out there, take some cross section measurements to know what you're working with. There's that 4 metre desirable offset, and you can see the truck there that would be about 2.5 metres wide, has sufficient space to pull over at the roadside and for the driver to open the door and get out if he had to. There we have an offset in the order of probably 2.5 metres, and it's not enough for that vehicle to safely pull over. So there's a school of thought that we should avoid offsets in this sort of range. Offsets around about the width of a vehicle. So perhaps 1.6 metres through to 2.5 metres is one range that gets bandied about. So some people think that you should avoid offsets in that range because it appears to be wide enough for a vehicle to stop and shelter, but in fact it's not really. And you can see that in that image on the right, the vehicle travelling away from us has shifted its lateral position towards the middle of the road to avoid that truck. there was a vehicle coming the other way. So there's increased risk of head-on crashes and other crash types where this is the case. Now, the risk is increases with the length of barrier at an offset in that order. So if that was a relatively short installation, perhaps no big deal. If it was a continuous length of half a kilometre or more at that same offset, more of an issue.
So Jamie, in that scenario on the right there, are you saying that one school of thought would be to actually put the barrier closer to the travel lane there if you couldn't go further away?
Yeah, that would be an option. Yes. So it's not a location where you'd want to encourage someone to pull over. So perhaps if that barrier was at 1.5 meters, that would deter someone from doing that. But look, it does, it really does depend on the specifics of your site and what else is happening there. The greater the width we can provide, the less likely our nuisance impact. So that's one thing. For maintenance purposes, an offset of this type would be good. If you have a lot of cyclists going along the road, providing more space is a good thing. It's a bit hard to tell what's going on from this picture. It may be that the barrier peters out just past the truck, in which case there's no big deal. But if it was a continuous length at this same offset, you might want to reconsider your offset or look to provide a refuge bay and sign it as a preferred location for someone to pull over.
Okay. I might pop up a poll, Jamie, just to see how people are tracking here on. Now, I'm pretty sure we've certainly covered off this, but remember, you're not being marked on this, everybody, but we're just keen to have a little bit of a chat about it. Which of these does not influence the length of need of a barrier? Protected width, flaring, post spacings, or barrier offset? Which of these does not influence the length of need? Now, Jamie, I'm just thinking through this for different jurisdictions, whether I've, I think it's applicable for all jurisdictions.
Yeah, I think this still holds.
Yeah. So just, have a guess in there. So which of these is not influencing the length of need, which Jamie went through? Protected width, which is the size of the thing you're protecting. Flaring, which is that angle you put at the end of the barrier. Spacing of any posts, or the offset, so how far it is from the edge line. Got a good few votes coming in. And these are the type of questions we'll be asking in the quiz, which you've all been doing well. I apologise, it wasn't quite live at the end of the last session. I've checked this session's one, which will be available for you to jump into as soon as you go. All right, we've almost got everybody. I might just give you a couple of seconds to have a guess. And okay, I think we've got, oh, there we go, we've got. Okay, I've ended that one, and let's have a look. Well, most of you, 12 of you are correct in the post spacing. So the protected width, so you're going to need a longer length of need, so the bigger, wider the thing you're protecting. The flaring, as Jamie I think showed in one of the diagrams, can reduce the length required. And the post spacing will influence the amount the barrier deflects, but not the length. Sorry, the amount it'll deflect, but not the length that the barrier the length of need, and the offset will definitely change the length of need. The closer you are to the hazard, the less the length. Anything to add there, Jamie?
No, that's the key. How close the barrier is to the hazard really determines your length of need using the angle of departure method. So the protected width and the barrier offset, sort of in combination, are used to determine your length. But you might have a hazard 10 metres from the road and the barrier 3 metres in front. That would give you the same length of barrier as if the hazard was 20 metres from the road and the barrier was 3 metres in front, if that makes sense. So it's how close your barrier is to the hazard, because geometrically it's the same situation, regardless of your protected width or hazard offset.
Very good, thank you. And yes, that flaring, you're sort of almost wrapping it around a little bit to try and cover off that angle. But you're not bending, you're not curving it, you're just flaring it.
Yeah, and there are two ways that we flare barriers. One is just flaring the terminal, or providing a slight offset within the terminal length. So that's pretty minimal, and you wouldn't sort of assume a reduction in barrier length through that type of flare. But if we were introducing a radius into our barrier and sort of continuing it further away from the road, that will effectively cut off our run out angle sooner and mean that we can get away with a shorter barrier length.
Good, thanks, Jamie. And yeah, thank you to all those who voted on that poll. And keep your questions or comments coming in through the Q&A, or feel free to pop your hand up at any time. Let Jamie continue on, and we might pop in for another question at some point soon.
There's a barrier at basically a 0 offset from the edge of the road. The roadway drops away pretty quickly, and there are hazards quite close to the edge of the road. So perhaps there wasn't an opportunity to locate that barrier much further from the road than it is, but this particular barrier is subject to very frequent nuisance impacts. And because it's a wire rope, that means that the barrier may well be ineffective next time it's struck in that area. Posts are knocked down, cable tension is lost. So I'd suggest that the choice of system here was not the best. A guard fence product would have been preferable. This design drawing demonstrates the old philosophy of choosing barrier offsets, and that was to locate your barrier as far from the road as possible. And this is where we were designing barriers around isolated hazards rather than continuous barriers, which is the direction that we're trending to. So the philosophy was locate your barrier as far from the road as possible and as close to the hazard as possible. That meant that you could get away with the shortest possible barrier length, but it did result in barriers being located at all sorts of weird and wonderful offsets. So along this particular section of road, we've got a barrier, bottom of the page here, at 5.5 metres. Here we've got one at 3 metres. This one's 6.1, and as you stepped your way along this road, you had 5.2, 4.3, 7.1, and so on. So aesthetically, it looked a bit strange. It did result in some barriers being located quite away from the edge of the road with a grassed batter in between. So there was a rollover risk. This section of road in the last 2 or 3 years has been upgraded now with continuous barriers. So marrying up the new approach of continuous barriers at 3 and 4 metre offsets to this old approach created some headaches for some, and really showed the change in thinking that's come about in the last few years with barrier design. The presence of embankments, curbs and cuttings may well influence your choice of barrier offset. Where you have a curb, we know that a vehicle that crosses a curb, particularly at high speed, its trajectory changes. Its bumper rides up and down before it gradually levels back out to its normal height. We want to avoid locating barriers at positions where that vehicle is not at its normal height, because there is an increased likelihood that the vehicle will vault over the barrier or perhaps even nose under the barrier. So to avoid that happening, we have some choices. We can locate our barrier as far from the road as possible. So we're aiming for that vehicle to have bounced up and down and flattened out before striking the barrier. That's all good and well, but it's really the case that we have the space to do that. If we have a curb, we're probably in a built-up environment. We have a nature strip, we might have footpaths, trees, poles, all sorts of things. Or if we're not in a built-up environment and we have a curb, it's probably in a cut and we have limited width to play with there. So the more common scenario where we have a curb is to locate the barrier as close as possible to the back of curb. So we're aiming to contain that vehicle before it's had a chance to ride up. So there's our barrier, back of curb. Often we've got subsurface drains and other things that might make that difficult, but the philosophy generally is to locate as close as possible to the back of curb. There may be a magic window somewhere in between where the vehicle has bounced up and has come back down to its around about its normal height. I'm unsure if there's any guidance around that in New South Wales or if that's an approach that's taken in Victoria. There's some confusing guidance around this, and it depends on speeds, and there's magic windows in the order of 1.2 to 1.8 metres from the back of curb that is there as an option if we can't achieve this a long way from the back of curb or at back of curb. Someone may be able to provide me the answer on that. Similarly, at embankments and cuttings, we want to take out the effect that those features have on a vehicle's trajectory. So there are some no-go zones in terms of locating barriers in relation to batter hinge points and inverts of drains. So these hatched areas here indicate where a barrier should not be located. So here, the cutting, and here on the fill batter. So we basically want to have that barrier located on the verge before a vehicle has had the opportunity to change its trajectory. That gives us the best chance of effectively capturing and redirecting that errant vehicle. The preferred batter hinge point offset differs between different systems. For guard fence products, we can typically get fairly close to the hinge point. So for a semi-rigid or a flexible guard fence product, we can get as close as 500 mil, or in the case of some of the flexible guard fence products, less than that. Some of the products have been tested as close as 300 mil from the hinge point. Where we do get close to hinge points, consider installing longer posts, especially where the batter beyond the hinge point is steep. The proprietary products and public domain systems have some longer post options that can be used. In the case of wire rope, which deflects more, and where we have concrete footings, we typically need to provide a greater offset from the hinge point, typically at least 1 metre, and desirably that full dynamic deflection, which might be 3 meters or something like that. So it's not something that's commonly provided, although it's desirable to do so.
Maybe we've got a comment that's come in. It's a bit more dealing with what we sort of covered earlier, but I'll read it out. We might sort of pause and talk about it and then come back to about a hinge point stuff. But it's associated with the retrofit jobs where we're creating a wide centerline treatment and trying to minimise the cost, so earthworks and or anything like that. So the edge line is somewhat moved towards the roadside, so shifted laterally there. And the concern is the safety issues or considerations that this might bring up. So in terms of shyline or alterations to length of need, points of need, or those sorts of things. Any comments on that, Jamie?
Look, yeah, it's a real balancing act. Obviously, the desirable thing to do would be to at least maintain your existing shoulder widths or increase them to a desirable amount. But it sounds like you're constrained in terms of space or budget, and putting in a central barrier does provide good bang for buck. It prevents those cross carriageway crashes, and also a fair proportion of runoff road crashes, those that sort of initiate with someone crossing a centre line and overcorrecting, that type of thing. But it always does raise alarm bells with me if we're pushing traffic nearer to hazards at the roadside. So your available sort of length of need to hazards is sort of reduced effectively. You're putting traffic closer to hinge points and increasing their likelihood of striking a hazard if they do depart the road. So look, it's very much a case by case situation, but if you can maintain the shoulder width, if you can't put a barrier at the roadside as well, look to maximise the shoulder width you have and think about measures to increase delineation and reduce the likelihood of someone departing the road. So that might be rumble strip edge lines and increased levels of delineation, that type of thing.
I think most of so the question was more specifically around wide centerline treatments, not necessarily with barriers.
Right.
But all that I think
Okay.
still applies. This might have a little bit more room to play with because there's not that physical barrier in the middle there.
Yeah, sorry. No, I had a centerline barrier in mind, but yeah, it's essentially the same principles.
Yeah. And I think my sort of just to follow on from that, I think your consideration of traffic volumes and things need to come into play. And just as the person who's popped this in has said, assessing it properly and considering all these things with a level of knowledge about the implications of these things, I think is important. And we do certainly know that there's big, holistic statewide programs and things which are not considering the individual aspects of different sites and the like. And they're the principle they're trying to achieve is some separation for these high-speed roads. And so it does come back to a case-by-case assessing all of these things in the context of the road that you're working in. And so there's a fair bit of work to do in those sorts of programs.
Yeah, look, the desirable thing would be to provide full containment by installing a barrier down the middle of the road and at the outer verges. And the New South Wales aspirational cross sections for 5-star roads show that type of arrangement. But it's often very difficult to achieve, and there's a high-profile road in Victoria where the road reserve is narrow. There are continuous trees at the roadside. There was very limited scope to widen the formation, and the decision there was made to install a narrow wide centre line, but with continuous barriers at the outer verges. So there's simply not the width to then go and retrofit a centerline barrier down the middle. So you precluded that sort of preferred ultimate cross section, but that was deemed the best outcome for this piece of road based on the constraints.
Thanks, Jamie. And if anybody has any specific site examples they want to talk about next module, feel free to send them in.
Little video here that demonstrates that barriers can and do work when they're located close to hinge points, provided the system is provided enough lateral support to the posts. I'll play that just one more time. You can see there a wire rope located very close to that vertical drop. The vehicle's struck it at speed, and it's been captured and redirected because that one set of wheels, the inner set of wheels, remained on solid ground. Allowable batter slopes. There are slopes, as we've discussed, that present hazards in their own right. So anything steeper than 4 to 1 is a hazard that we should consider shielding. Any batter that is no steeper than 10 to 1, so that's really quite flat, is suitable for a barrier to be installed anywhere along it. In a retrofit situation, we might consider installing a barrier on a batter in the order of slope in the order of 5 to 1 or 6 to 1. And this snip from the Austroads guide shows a barrier here located at the base or beyond the base of a 5 to 1 batter. And it suggests that if you've got a slope of that steepness, that you should locate your barrier beyond and put a relatively flat pad of 10 to 1 in front of it. This is not something that should be encouraged. It would be preferable to locate the barrier at the top here on the verge. And if we can't get a desirable offset there, we might need to do some earthworks to get our, say, 3 metre offset. Locating the barrier down here really does open up that opportunity for the vehicle rollover. Another video. This vehicle obviously not contained and redirected. Why was it so? This angle tells the story. You can see that wire rope located just beyond the invert of the table drain, and I'll play it again. The vehicle has gone down the side of the embankment and nosed under the barrier. As it's hit the invert of the drain, the suspension's kicked in, the bumper height at that front corner has gone down, and it's penetrated straight through the barrier with a fair bit of speed still. So the moral there is to avoid any interaction between barriers and changes in slope. Barrier deflection. How much is our barrier going to move upon impact by an errant vehicle? Now, Evan stepped you through the different crash testing, or the MASH crash testing protocol and the different test levels and so on. As a result of the crash testing process, there are published deflection values for each system. Rigid barriers, we know, deflect by next to nothing. Guard fence, so this applies to your public domain G4, which is now a legacy product, and also to your Thrive-Beam products. They will deflect by about 1 metre. You can stiffen them up further by closing up the post spacings and get that deflection down to about 0.5 metre. Our flexible W-beam products, so that's our Easy Guard, Ram Shield and Sentry Barrier. they deflect by about 1.6 meters in the 100 kilometre per hour crash test. So they're all TL3 products. The numbers differ slightly between the products, but they're all ballpark 1.6 meters. So that's about the number you need to have in mind when you're dealing with that product and locating it in relation to your hazards. So barrier deflection and barrier offset, these two choices go hand in hand. Your hazard is a certain distance from the edge of the road. If you're putting a barrier in front of it, some of that distance will be shoulder and the rest will be there for barrier deflection. So it can be a trade-off, especially in constrained locations. And where things are particularly constrained, you may tend towards a more rigid system that deflects by less, or at least take measures to stiffen up the system, reduce the post spacing in particular. Wire rope systems, again, there's some differences between the products in terms of how much they deflect, and it's a bit tricky to compare apples with apples because the different crash tested configurations, they're different. The post spacings differ and the length that's being crash tested might differ by a little bit. So the shorter a barrier length is, the less it will deflect. That's for wire rope. And the closer its posts are, the less it will deflect, because even though they sort of work largely through the tension in the cables, the posts do provide some resistance. But 2.2 meters plus, the longer it gets, the more it deflects. And if we're on the convex side of a curve, so on the inside of a curve, the effect of the tension in the cables is that we're looking to pull that cable in and away from the road. So in those situations, we expect the barrier to deflect by even more again. And we can see deflections of 4 meters and beyond, where we've got long installations and or on a curve. Clearly not enough space for deflection of that wire rope there. The post spacings have been closed up to perhaps 1 meter, so its deflection will not be to that maximum amount. We're also in a built-up environment, unsure of the speed limit, but it might be 60 perhaps. So if vehicles are doing 60 k's per hour, we're not going to see those full crash-tested deflections, but even still, we don't have enough space for deflection between the barrier and that pole. Probably a guard fence product, W-beam product, would have been a better choice here. There we have a rigid hazard right up against that barrier again. So that's not desirable. An effort there should be made to remove or relocate that object, stiffen the system up. But you can see, we've got a bit more deflection between the barrier and this tree here. At this location, there's also a number of other hazards off the photo here that are adequately shielded. So this barrier is doing a good job at shielding most of the hazards here. We have one where a little bit more effort might have meant that it was better shielded. Another situation where we don't have any space for deflection. It is a tri-beam installation, so its deflection will be less than a G4, say. It's on the inside of a curve, and again, there are other hazards that you can't see that are adequately shielded. So, look, this barrier, whilst it's not sort of by the book, it is providing some benefit in shielding that pole, and it's perhaps just about as good as you could do, short of relocating that pole, which, as we know, is an expensive thing to do and would be unlikely to happen.
So, Jamie, just a couple of questions that have come in. So one's around nominal AADT for continuous barrier installations. on the shoulder or for containment. I might talk to that a little bit with the New South Wales document. The version I've got is probably a little bit old, but the philosophies will still remain. So I may come back to that unless you want to add something there. And the second one's about the availability of the crash test videos that have been played, whether they're online somewhere. A lot of them you can get from Google or YouTube or Googling Google video search. But if there's particular ones you're interested in, let us know and we can make sure those ones are provided to you.
Yeah. Did you want to talk to the AADT, Ken? Or
Yeah, okay. I can do that now briefly. So I might just find that document. Sorry, bear with me, Jamie. Oh, yeah. So hopefully you're seeing that Word document there, are you, Jamie?
yes.
Yeah. So at a very sort of a high level sort of treatment philosophy perspective, this is what New South Wales Centre for Road Safety has really been pushing, which is to take into account both the exposure being the AADT and the crash likelihood being a fatal serious injury per kilometre crash rate. And then these ones up there in the red are where we'd be expecting to see that continuous barrier system rolled out there. But then it goes, this document goes into a bit more detail in terms of giving you a little bit of a, oh, there it goes, some determining the safest cross-section flow diagrams essentially, or and you can look there at different volumes and look for the corresponding cross sections that you have as an aspirational cross section. You may not be able to get it throughout that whole route, but then you start to see these sorts of tables with some information around the cross section features, the seal width, and what would be expected. So. And then you can sort of see the indicative star rating. Now, there's a bit more involved in getting an actual star rating to it. We do star rating of roads, but this is a pretty good indication of sort of where you'd be expecting to get with a star rating. So I'm not going to go through this whole document, and as I said, this one's probably a little bit out of date. So it'd be worth following up with the Centre for Road Safety there for the selection of safer asset cross sections on a high-speed roads document. So hopefully that helps some people out, because yeah, there are quite a few I suppose intricate decisions to be made, and a bit of guidance is helpful.
Thanks, Ken. So next step in the design process is to think about our minimum length requirements. Now we do need to check that regardless of our our length of knee that we've determined, that we're satisfying the minimum length requirements of the barrier system that we have in mind. And you might be surprised to see what some of those minimum lengths are, and they have increased with the shift to the MASH protocol. So for wire rope products, and these numbers are spelt out in the product acceptance sheets, and they're based on the crash tested configuration. For wire ropes, those numbers are 160 to 180 or 90 meters. So they're really quite long. The flexible W-beam products are quite a bit shorter, but still not very short, very difficult to achieve in some constrained locations where you've got lots of driveways and this type of thing. W-beam products like a G4, you could get away with a relatively short length say 10 metres between terminals, and those terminals might be 15-metre approach terminal and a 5-metre, a 4-metre trailing terminal on the other end. So a minimum installation length sort of as little as 30 metres or something like that. So these numbers are all given in the product acceptance sheets. Look, it does happen on occasion that barriers are installed to shorter lengths than these. It's not preferred, but if the choice is to not install any barrier at all, you might install a 50-metre long flexible barrier, flexible W-beam barrier. It's not by the book, but I would argue that that's providing a better outcome than not providing any barrier at all. But do be mindful of these numbers, and it might influence your product choice. That installation certainly doesn't meet minimum length requirements. It's basically an approach terminal plus a single rail of guard fence, 4 or 5 metres, plus a trailing terminal. And you do often see these token lengths of barriers at small structures. This is a stock underpass, but it might have been a small bridge or a bank of culverts. The desirable thing here to do would be to think about think about the location of the hazard at the roadside, and that might be the waterway or the drop. How far is that from the edge of the road? And work back from that to ensure that your barrier cuts off your run-out line, so to provide a length of need. And also on the departure end, because this is a two-way roadway, we shouldn't be installing that trailing terminal. That's a hazard if struck end on, and perhaps the defence was that this was installed outside the clear zone for the opposing direction of travel, but we're going away from the clear zones, and it's always preferable to install an energy absorbing terminal where there's a possibility that it might be struck end on. I mentioned this idea of a run-out area. The run-out area is defined as an area, as you can see there, it's 6 metres wide and it's 18 metres long, measured from the point of need. It's the same for wire ropes and for guard fence products. And that area is to be kept free of fixed hazards and to be relatively flat. Doing that means that any vehicle that just misses the start of the barrier can pass through that relatively forgiving area. A vehicle that strikes near the start of the barrier, the gating portion of the terminal, can pass through and might come to rest, and they typically will come to rest within this defined area. It also provides space for the system, and particularly extruding type guard fence systems, to operate free of interference from any other hazards. So an extruding type terminal that's struck end on is going to spit the rail out to the side into this area, and the vehicle will likely sort of rotate around and then come to a stop in this area. So in a new road project, you may wish to provide a relatively flat pad, for want of a better term, as a run-out area near the start of a proposed barrier. In a retrofit situation, you may do some earthworks to provide this, or it may influence where you start and stop your barrier. We obviously need to think about our length of need, but it might be the case that if we extend our barrier just a little bit further than that, we can achieve a nice run-out area in the vicinity of the terminal. Any longitudinal system needs an end treatment. They have two functions. They need to be crashworthy. If struck end on, they need to be able to safely contain and bring that vehicle to a stop at high speeds, potentially, up to 100, 110 kilometres per hour. On the left there, you can see one of the new breed of impact absorbing guard fence terminals. That's the ETSS, I think. On the right, we have a now superseded or legacy wire rope product, but most of the wire rope terminals are similar in nature to that one, in that the cables sort of increase in height gradually from the anchor point. Wire rope terminals are in the order of 12 metres long, and that entire length is considered gating or not redirective. So you need to find or have available an extra 12 metres or thereabouts of space for a wire rope terminal to ensure that the barrier will adequately shield anything behind it. So that can be something that counts against wire rope systems. Guard fence terminals, on the other hand, their point of redirection is partway along the terminal, and it's nearer to the anchor point than the far end of the terminal, typically about 4.5 or 5 metres from this anchor point. So you've got 4 or 5 metres of gating terminal as opposed to 12. There are differences, again, between the different guard fence terminal systems in terms of where that point of need sits. And it's typically at a post 3 or something like that. It might be if you're constrained and you can't get the length of need that you would like, you might choose the product that has its point of redirection located as close as possible to this anchor point, so that you're providing the best protection you can in your particular case. The second function of a terminal or an end treatment is to provide anchorage. So it's anchored to the ground here by way of a cable and a bracket. So this allows the system to stand up effectively and accommodate the forces and the tension that's developed in the system when it's struck side on by an impacting vehicle. That's the MSKT, the MASH SKT, one of the newer MASH accepted products. It looks quite a bit different to the last one. It's quite a bit wider. Some don't like it for that reason, but it's probably the simplest of the 3 currently accepted products in terms of number of components and installation. So each of the 3 products has their pros and cons, and one may suit your site better than another. When they're struck, they're intended to end up like this. So this terminal has, with its extruder head, has spat the rail out to the side, brought the vehicle to a stop over a distance sort of from here to here, up to about 15 metres. And that's what it looks like from another angle. Barrier transitions. Now, I will explain that this is a one-way carriageway where the direction of travel is towards us. So this is this vehicle is facing in the wrong direction. We would not expect a vehicle to travel in this direction and through this gap. However, that said, this overlap is not sufficient. The point of need of this wire rope system would be about here. The point of need of this guard fence system, now that is an old breakaway cable type terminal with timber post, fully gating, 10 metres gating length. Its point of redirection is down here. So we've got a length of, perhaps 10 to 15 metres of roadside that is not shielded effectively. So desirably, there would be a greater overlap between those 2 systems to ensure that an errant vehicle couldn't pass through the gap. Now, as you can see, we're on quite a high fill batter. To have achieved that desirable overlap would have meant quite some earthworks. So I can see from a constructability point of view why it's happened that way, but from a safety point of view, it's not great. Some of the RMS standard drawings deal with barrier transitions and how to provide overlaps between, particularly between wire rope and guard fence systems. And the preference is to overlap those points of need, have them overlap by at least 1 metre, so that there is not that opportunity for an errant vehicle to pass through the gap. Here's an overlap where the points of need are probably overlapped. So it's okay from that point of view, but the two systems are located very close to one another. Desirably, the distance between the two systems should be at least the crash-tested dynamic deflection of this upstream system. So for a wire rope, that might be 2.2 metres or more between these systems. Here we've got much less than that, less than 1 metre. Now, some people argue that it is quite close to the anchor point, so you're not going to achieve that full crash-tested deflection, which is true, but desirably we should certainly have more than's been allowed for there. Perhaps the fact that this is an impact absorbing, energy absorbing type terminal reflects that they know there isn't enough space there. And there is a possibility that an impacting vehicle that hits the wire rope will also clip this terminal. If this barrier behind was located well clear of the wire rope, we could get away with a trailing terminal in the knowledge that it was shielded by another barrier and wouldn't be struck.
That would be a significantly cheaper option, would it not?
Certainly would be. So this is a legacy product, but off the top of my head, and someone else might correct me, there's something like $4,500 or something each, ballpark, as opposed to a trailing terminal, which might be $500 or $1,000, something like that. At concrete barriers, we can transition a W-beam to concrete directly. In New South Wales, the standard arrangement is to use a thri-beam, but the principle is to gradually transition the stiffness of the barrier from the semi-rigid system to the rigid concrete. And in the image here, you can see that's been achieved by closing up post spacings to 1 metre and then 0.5 metre. There's actually a double nested rail to further stiffen things up for this connection. So we can have direct connections between semi-rigid and rigid systems. There are no direct connections to wire rope products.
In New South Wales, I think it's thri-beam there, isn't it? That connection?
Yeah, that's right. So there is a standard detail for that thri-beam connection in one of the RMS drawings. So a few parting tips. If you're designing, know the ins and outs of your chosen barrier system. And don't go into a design with the blinkers on. Keep an open mind. You may well find that because of constraints at your site, you can't get the system that you might want. There are lots of trade-offs in design. You're balancing hazard offset from the road, accounting for deflection, desirably working within the existing formation, but maybe needing to do earthworks, lots of things to weigh up. We've seen the minimum length requirements for different barrier systems. They are really quite long. So if you see a barrier that looks quite short, chances are it certainly doesn't meet those requirements. We should avoid short breaks in barrier wherever we can. The terminals are the most hazardous and the most expensive part of a barrier system, even though they are crash tested and accepted to MASH standards. There is potential for injury to vehicle occupants. So if we can minimise the number of terminals, we're providing a safer outcome. You may well find as well that instead of providing successive lengths of barrier, it might be a cheaper option to link them up and only need 2 terminals instead of 8 perhaps. Even though you've got a longer length of overall barrier, it may well be a cheaper solution because those proprietary terminals are quite expensive. Flaring of barriers is something that should be done more, especially where our offset isn't what it should be. So if you're dealing with a barrier offset of, say, less than 3 meters, I encourage you to flare the terminal away from the road so it's located more than 3 meters. That has benefits in terms of shy effects. It can open up sight lines if your terminal is located near a driveway. Lots of benefits to flaring barriers. Provide run-out areas where you can, so that might influence where you choose to commence a barrier. Be mindful of all those existing assets at the roadside and reinstating the ones that need to be reinstated, like signs and light poles and the like, ensuring that they're located, when they are reinstated, they're not located where they might sort of have an undesirable effect on the operation of the barrier. So outside that run-out area, certainly not just in front of barriers, where a vehicle might strike them as well as the barrier, and where they might deter a person from pulling over at the roadside. There is a list of things, as long as you're armed, that you need to be mindful of when you're doing a barrier design, and it very much is a site-by-site situation. If there are bridges and culverts that you need to work around, identify that early. If you, by chance, need to provide a structural solution at a bridge, that's something that will be a time-consuming part of the process, and you want to identify early. You might need a ground beam to be designed and constructed before you can bolt down your barrier posts. If you've got culverts, you might want to fiddle your post spacings to straddle them. If they're a motorcyclist, and Ken will talk about motorcycle treatment shortly, you might want to consider providing a barrier type that best suits that road user. Are there pedestrians that we need to provide brakes for? Are there cyclists? And if there are cyclists, that might influence our barrier offset. We might want to provide a width that provides a safe and comfortable width for cyclists to ride. There are buses and bus stops and so on and so forth. So I will leave it at that, Ken, unless there are any questions. But we will step through some tricky situations and examples of real-world situations on Wednesday, where a lot of these things will pop up. So happy to take questions now or defer them till Wednesday.
Thanks, Jamie. Well, we'll just see if there's any questions that pop in. Otherwise, I'll get started. Nothing seems to be coming in at the moment, but we'll. If anybody does have any questions for Jamie, we might have a little bit of time at the end to cover that, or we can cover it off next week. Next module, I should say. All right, good. Thank you, Jamie. Time to have a little bit of a chat about motorcyclists and motorcycle considerations with barrier systems. And as I mentioned at the start, it's a hot topic often, and so we need to get our messages clear on this and base it on some research and evidence. Okay, and let's talk about some of the research that's been done around motorcycle crashes at barrier systems, and this has been done predominantly from the University of New South Wales, and you can see there that we've got different jurisdictions. If you look at the total, these are the sort of the fatal motorcycle crashes that were in their investigation and how many of them were barrier related. And you can see there that a very, very small percentage of the total trauma to motorcyclists is striking barrier systems. There's a bit of unknown there, and that's a bit of a police reporting thing and not giving us that information specifically as to what type of infrastructure may have been struck. But even still, even if you included that, we'd be talking, if they were all barriers, which we know they certainly would not be, but it would still be a very small percentage. So that's, I think, important to know from the outset. Then when you sort of drill down to, okay, well, what type of barriers in that small percentage, what type of barriers are the ones being struck that are killing and seriously injuring motorcycles? And we see guardrail systems are the most dominant, then concrete, then wire rope systems, and then it was undefined in the police reporting again. But I think I'll give away a prize here. I've got a couple of reasons why guardrails would be the highest there. And first people to write in any of the reasons I'm thinking will win a prize. So just type that into the Q&A and you're a chance to win a prize if you've got ideas why guardrail pops out as the highest there. Okay. This is good. Okay, well, we've got it, has come through a lot there. It's the most common. There's the most of them out there at the time of the research, and that's absolutely right. So I've got a name there, but I think it's their username, which has always confused me. Arosmet. Got it. I'll find out who you are and you shall get a prize. So that was one of them. There's a couple on there who have put in things about the posts, and that's, I suppose, part of the nature of it, but it wasn't really particularly what I was thinking. The other one that I was thinking, which was a little bit more intricate, but it probably related to the most common out there, was the fact that a lot of these crashes have been occurring on motorcycle touring routes, and there's this they're fairly windy routes a lot of the time, and there's just not the ability to put a wire rope system in those, and we wouldn't put a concrete system for other reasons. So let's keep the other thing about this research, so there's some people at University of New South Wales who have been studying motorcycle barrier strikes for a long time, and let me summarize a heap of research. About half the motorcyclists were sliding along the ground, and they did hit the posts as the comment came in. And about the other half were still on the bike, trying to stay on the bike, and they hit the barrier and they go over the top of the barrier very quickly. And so they're the kind of 50-50 split there. And I'll come back to that and show you a few sort of videos of how that plays out. I hope you've been remembering to count your Wallies as we went. There were a few that popped into Jamie's, I noticed. So we know that barrier protection, so underrun protection and the like, can have a pretty decent crash reduction in terms of some programs that have been rolled out with just barrier protection and underrun protection. So we know we can get some good gain there. It's about thinking about where you have higher percentages of motorcyclists. When a rider strikes a barrier system, the biggest source of death and serious injury is actually thorax. And the head is certainly an element that has a lot of challenge, but not as much as that thorax hit. So let me show you those two different crash types. So hopefully this will stream for you. So that one was a motorcyclist who's really almost off the bike. I'll play it again, off the bike really, almost trying to gain control, and you can see they go over the barrier very quickly. And the sort of the physics does that. So here's a crash test where you'll see that happen. And you can see that the rider goes over the top. The bike does exactly what we want, runs along the barrier system, but what we're trying to protect has gone over the top. So that's about half of our barrier crashes, something in that sort of scenario. The other half we see are riders that are off their bike and they slide and then they would strike a post. So hopefully that's streamed through to you. I'll play it again. So this one is what I call a low side crash. Off the bike, slides and strikes a post. That one, nice low speed, friendly crash. But this one's again a crash test where we see a bike coming in with a rider at the 60 km/h, and we see that the bike has enough energy to take out a post, but the post pretty much doesn't budge with the weight of the rider, and easily enough to kill the rider. So for the sliding one, at least, we've talked about it quite a bit already. We have different underrun protection devices available, and it's dependent on your barrier system that you're using, your proprietary product, as to exactly which one it is. So this one is the public domain one, which I'll talk about what New South Wales accepts for use these days, or what's legacy, and this would be actually a legacy product. But you can retrofit this. And so you could see here, you could imagine sliding along there at 70 km/h. You've come off your bike, and to hit one of those posts would be a extremely severe event. And then hitting this and sliding along it would be a less severe event. It would still be pretty violent, but it'd be much less severe. So that's what we're trying to do with these underarm protection. As I said, you can retrofit it to existing systems, so that's a good thing. And you can see the little brackets that they've just started placing before they're putting the rails up there. So you notice it's not on the end terminal, okay? And that's important because Jamie's talked to you about the specific functions of those end terminals. Evan talked to you about it, testing. If we were to start adding stuff and bolting stuff to that, it would potentially change the way it functions altogether, and may present a danger to a passenger vehicle that comes and strikes that end terminal. So we certainly don't want to be attaching that. Sometimes you get installers wanting to do that, and so we certainly wouldn't do that. Now, there have been some trials in some other jurisdictions, not in New South Wales that I'm aware of yet, of a poly buffer system. This one is, it's a plastic product that sits under the terminal that isn't connected to the terminal as such, and so it was deemed to be acceptable for the end terminal because when struck, it would be ejected out of the way. And there's a bit more on an X350 there. So the crash testing for motorcycles it's a European test. It uses a 80 kilogram crash test dummy with some little modifications. They certainly don't like being used as motorcycle crash test dummies because it is a lot of energy striking one of the posts. So I'll show some of the Transport for New South Wales Crash Lab crash test footage here for you. So here's a motorcyclist, 60 km/h, strike into a post, and you can see that pretty much writes off the dummy, and is certainly death levels of force put into that dummy. So with the addition of a underrun protection system, we see that the dummy's energy is deflected along the system. There's absorption of the energy too, and that runs along the system and washes off speed over time, which is a big win. And that's what we like to see. So we do know we've had some sort of very successful designs there for that 60 km/h European test. So it is 60 kilometers per hour. We know that there's some higher speeds than that, which is a bit of a danger. So hopefully those were streaming for you. I'm just going to check there. Okay, so the question that's come in there is any reason why the dummy is sliding head first? So it is a good question. The crash test, I suppose, was to try to replicate some of the higher severity crashes. It was the 60 kilometer per hour, so it could have got higher severity going higher, but that was seen as the most, if you could pass that, you're likely to pass other crash types because of the neck twist that happens during that crash type. So I think I've got some overhead views of that, so you can see, yeah, it is head straight. There's actually two tests that are done. One's directly at the post, one's directly between the posts, and interestingly, that between the post test with an underrun protection exhibits more force on the rider than the one directly at the post when you've got the rub rail there. I think it's something to do with the twisting of it back. There are then some attempts in different jurisdictions to try to address that over the top crash. We haven't done too well on that. There's different post cappings available, and I suggest you talk to suppliers if you're interested in post capping of one description or another, and just running that by Jade Hogan's team in their Centre for, the Transport for New South Wales, just to check you're good to trial something like that. And then we've got the wire rope systems, which the motorcyclists, some of the motorcycle groups will call the cheese cutter and somehow make out that it's the most dangerous thing there is for motorcyclists. Well, the research doesn't show that. The research shows that, like any of the barrier systems, if the motorcyclist hits the wires, they go over the top. And if they're sliding along the ground, they hit the posts, and the posts act pretty much the same as a flexible W beam. Where there is some truth into it is we probably don't have as good retrofit devices for motorcycle safety for wire rope systems. However, we don't put them in areas that are heavily populated with motorcyclists, like motorcycle touring routes and the like, because we cannot put that barrier on a curve radius smaller than 200 because of the tension, and posts would move into the road or away from the road based on that. These are used on long, straight roads, usually where fatigue is the issue, and it's passenger vehicles that are leaving the road in these run-off road incidents. The motorcyclists involved in other, some of the intersection crashes are more of a danger for motorcycles on those type of roads. There is a little bit of risk, but in the huge number of fatality and serious injury investigations, there's only been a handful that have involved motorcyclists hitting wire rope systems, and each of those has been a post-related issue. And we're talking, I think I did the figures at one point, it's like 0.02% of the issue is wire rope systems. So really, anytime I'm talking to motorcycle groups, and I spend a lot of time talking to motorcycle groups about infrastructure, I just urge them to put their attention to something that is a genuine issue for motorcyclists, because this is well known that it is not, and the credibility of any sort of lobbying around this doesn't really fly. So I think we need to do a better job of putting messages out there around that, and certainly I think the introduction of flexible W-beam systems provides us with a greater advantage, because I don't think in any popular motorcycle route we would be using wire rope. So I'll keep ticking on, and there's a comment in there that somebody's made that they have a friend who's been in an incident with the wire rope system, and and so there have been incidents, and I'm not saying there haven't. I'm saying that they're far fewer than there have been with other barrier types, and where I think we have some challenges is the way we can provide protection of the system. But certainly our most high risk locations for motorcyclists already have W-beam systems anyway. There's the other thing about any barrier system really is to remember the advantages that motorcyclists get from that barrier system, which there's some studies here that show that they were all wire rope system rope barrier system installations, which had significant reductions in trauma for motorcyclists as well as other vehicles, which was essentially stopping vehicles getting into a motorcyclist lane, so with a central barrier system. Now, yeah, I think we've got to be careful how we use that because, technically the motorcyclist would also have been protected with a concrete system or a flexible W-beam system as well. So I don't think we can say wire ropes particularly good. That separation is really important. So always something to remember. So what some jurisdictions have been doing, and Victoria is one, is trying to put some sort of post padding, post protector in there. And it's kind of the football goalpost padding. It's not as effective as some sort of underrun protection, but it is something. And so if you did happen to have a site in New South Wales where you thought it was high risk for motorcyclists or medium risk for motorcyclists even, and it was wire rope system, and you wanted to do something, you could look to investigate to trial some of these systems, and they've been used in a variety of locations. So there's some more. There are different suppliers that offer those for their wire rope systems if you're down that track. But take, for example, this road, which is the South Gippsland Highway. This would be a back-to-back flexible W-beam system with underrun protection now, for sure. Like if you're getting to the point where you've got enough motorcyclists that you are going to spend $45 per unit, I think the barrier system choice is the go, so you can get a really good underrun protection. And there's lots of different little products. Of course, we use a flexible delineator these days for any motorcyclist over the top that's not sliding along the system. And some dangers installation-wise. Sometimes they install it right on the post. We lose a whole lot of advantage for that cushioning. And we have gaps where a leg or an arm can get through there, and that's a big danger there, because it's the post that'll do the damage. So just have a look at how they should be installed and make sure you do that. And try to close up these gaps here is important. So products accepted for use in New South Wales: Biker Shield, Hyasa Rail, MPR on EasyGuard Smart and G4. And the legacy product is your public domain underrun protection system, which is a legacy product. Some of the other non-approved ones that are out there, though, that you might consider trialing if the circumstance arose. I talked about the terminal protector there, the post capping of different descriptions. Not sure I would actually trial this one. Let's not have that in there. That's a fabric system that gets pinned down to the ground. There's some maintenance challenges with that one, and potentially, as we said, some of these cushion post protectors, and there are single point protectors as well that you can look at. BikerMate, Impact Protect. If you have a specific hazard and it's particularly concerning for motorcyclists, something to consider. So I should say I'm a licensed motorcyclist myself. I'm not an active motorcyclist. I certainly there's a lot of dangers out there in riding, but I think there's a fair bit we can do with our barrier system choice and the addition of underrun protection and different products to get as safe an outcome as we can there. So there was a few insights there, and certainly I'm happy to talk more if you have specific locations where you've got concerns and what could be done for motorcycle safety, happy to have a look at that. But that pretty much gets us to the end. And sorry, I ran a little bit a minute over. But what we would like is you to send in email through any photos or a location or a plan that we can talk about with you next session. And do your quiz, which is live now and ready to go. And I think that's all. Thank you, Jamie. And thank you, everybody, and enjoy the rest of your day.
Cheerio.